Hi folks, and welcome to the session on Cloud Native Serve Two Ways with Kubernetes and serverless. My name is Karthik Gaekwad, and you can follow me on Twitter where I'm iteration1. So our official Oracle Safe Harbor statement. And going into the actual content, when we kind of first started out, the old world of our industry was where we had proprietary systems and software, which were kind of like bundled together, sold as a single unit. A lot of us think of like the mainframes over here, where everything was kind of siloed away, and the system analysts had evolved and became, very vital to the actual system health, like we show in this picture. I don't think there's a lot of us that were have been in industry that long, but when I kind of started in industry, this became more of our stereotype, where we had more of web applications kind of made, that were kind of stored in a data center in your company. I remember when I first did my interview at my very first job, one of the cool things about being in IT was they would tour you down into the actual data center that was there at the campus. So it was kind of interesting from that aspect. This kind of evolved into more of a DevOps kind of standpoint, and there was a lot of friction between different teams at the time. So DevOps kind of made an evolution over here. And so stepping into it, DevOps is where development operations kind of came together, and this gave rise to the modern system analysts, like we like to call it. Developers thought more in terms of deployment and not necessarily in terms of code anymore, and it made DevOps help with a cultural shift, as much as it's a technical thing that's become prevalent today. With that, DevOps comes with the cornerstones of DevOps are the principles of CANs: culture, automation, measurement, sharing, and lean. And it brought about a bunch of different things, which was continuous integration is one of the big things and big evolutions that DevOps has brought to industry, as is continuous delivery. Some folks call this continuous deployment as well. And from a development standpoint, it's become more microservices. More folks kind of use containers, and cloud adoptions really help DevOps also kind of push this forward. So if we took a look at a very stereotypical application, back in the day, this, is, I say, monolithic applications or, stereotypical applications. And there's actually still folks in the industry today that have like monoliths that they're trying to move over. But typically these applications would have a lot of users. There would be, one app with, a really large code base, might have, dozens or, hundreds of modules potentially, and a lot of them would end up talking to the database. So one of the evolutions that we've had here is that these applications, might be one thing and they might do many things together. I remember when I worked in e-commerce, our catalog application, our cart application, checkout processing, parts list, quoting, all of those things were kind of put together as one single app that was deployed. Over time, microservices has become, very popular, and this has become more like de facto. And a lot of this has kind of evolved because it's really hard for your feature team to be able to ship software quickly to users in production. And when you have a monolith, everybody has to come together to say, hey, does the build actually work? Can we deploy this today? Something broke. How do we go about fixing it, etc. So microservices kind of gives you easier and a more de facto way to deploy cloud native software. It's based on the 12-factor app paradigm. So if you haven't heard of this, go check it out. It's really important. I think it's 12factor.net or 12factorapp.net. You should be able to just Google that. And it gives you these principles that allows you to deploy and scale your applications in a much simpler way than before. But one of the drawbacks, and we're seeing this a lot today, which with a lot of people going into microservices, which is that it's become difficult to manage and monitor and puts more onus on the operations side of the team or operations side of the house or the DevOps side of the house, as well as the feature teams or the developers writing the code as well. So this is just a quick example of a microservices application. You might have this thing is written in Python, the same in Java or Go, etc. And if we kind of look into this a little bit more, line 1 and 2, it's basically importing this Flask from Flask, and then lines 4 through 6 is basically giving you a route to an endpoint called data, which returns some meaningful data, and then the last 2 lines here kind of help you actually run the application on on localhost basically. So this is just a quick example of microservices. This is more of a code session, so I wanted to have some code out there so we're on the same page. And I talked about monoliths earlier in terms of e-commerce, and if you think of this as a microservices kind of application, here we still might access the same database clusters. A lot of leading organizations will kind of split this out from a database as well, but then your application is actually running. Your orders application is different from your cart application, which might be different from your reports and catalog, etc. So this is, a simple high-level abstraction of how microservices might work. And from a code perspective, a lot of folks are writing microservices today. From an infrastructure perspective, this also kind of gave rise to this idea of containers, where containers is more of like an OS virtualization primitive. It appears as to be its own standalone system with its own root file system. And it's a really great way. One of the reasons people really like it is that you can deploy software components and their dependencies as one unit of deployment to a host or to many hosts, etc. But if you really peel back the onions, and if you really look at this from a Linux perspective, it's not really like a thing in Linux. It's more of it's a combination of a few things. It's a combination of namespaces, control groups, and some OS features behind the scenes. And you could actually do this before Docker, the company, came around, but there was a lot of things that you had to do together to actually make this work. The big evolution or revolution in this space was when Docker arrived. And Docker really helped us kind of change the way we build and ship software. From a high level, Docker lets you package your applications in a different way, allows for dependency management and runtime configuration. And also, containers just become an implementation detail at the end when, you Dockerize your application and kind of throw them into a container. So and the other big advantage here is your app is actually decoupled from the host that it runs on. It just needs the Docker engine for it to run on top of. So that way it allows for portability. So you can take your application running on one machine and potentially transfer it onto another machine or redeploy it to another machine in a really easy manner. So this is a quick example of what a Dockerfile would look like. We can use the example that we talked about before with our little data pie service that we had. And so this, I'll go into just the actual code itself. The first couple of lines here, we're starting with a Dockerfile. And so that starts with, since this is a Python example, we start with a base image of Python 3. We're doing a couple of apt-gets to make sure we have the right OS version installed and all the patching stuff done. And then we create a worker, line 4 over here creates a worker of app. And we're, pip installing Flask like we did before. And we're copying a specific data services.py file, which is, you can think of this as the same example that I'd shown before. We're also exposing 5000, and this is because the application it's a web service. It'll be exposed on the port 5000. And the very last command, line 12, is actually running the service. So Python 3 startup data services.py. So one of the good things about Docker is that it does allow you to run applications independent of what host it's on. The problem is, we're software engineers, and we really like this idea of pushing things that we write to further and further and see how things break. So if you're just doing development with Docker on your local machine, works out great because you might just be running one or tens of many containers on there. But then when you decide to say, hey, Docker works great, let's push this to staging, or let's push this to production, etc., we start to have a lot more hosts involved in here. So we kind of push this to a prod setting, and it's really hard to kind of figure out where we are from a container, and what host it might be running on. So when you do have trouble with some container not working on some specific hosts, and you have many hosts, it's really hard to figure out where the problems are and what's behaving badly. So this is where Kubernetes kind of plays a vital and important role. You can think of it as a container orchestration or container management at scale. Here we say Kubernetes provides abstraction for deploying software in containers at scale, and it leverages automation and a declarative kind of configuration. So if we step into this a little bit more from a terminology setting perspective, Kubernetes is just a set of containers that are scheduled as pods. So they're a lot less container. We call them pods in Kubernetes. And multiple pods and other components can be defined in a deployment. So when you're actually deploying something with Kubernetes, the smallest unit is actually a deployment. And when we want to expose our applications, to the world, so for example, in the past application that we had, that data service.py file, we wanted to use port 5000 to expose that. So instead of doing that, we would say, hey, use a Kubernetes service, like a load balancer, or you can use other services as well inside of Kubernetes to expose those applications to the world essentially. So if you think of Kubernetes as a platform, it allows for infrastructure resource abstraction, clustered software with one or more masters controlling worker nodes. It has a scheduler inside of it that helps you deploy work to the different nodes with various patterns. And cluster configuration and maintenance does have a learning curve as well. So I put up this architecture diagram because a lot of times folks kind of end up asking, hey, you talked about scheduler, like how does it work, etc. And so, this is kind of how the Kubernetes architecture works. You have a kubectl or a kubectl, which is the command line interface that you end up talking to when you're trying to do deployments, etc. You might have a master node where you actually have Kubernetes kind of deployed in. The master node has the API server that kubectl talks to, and has the scheduler that allows for tasks to be scheduled to specific worker nodes, etc. And it has the controller manager, that allows for service accounts, namespaces, etc. The worker node here is actually where your pods end up getting deployed to. So your application, right? So for example, your e-commerce application or the data service.py container, etc., would actually get deployed into your worker node. Typically, we end up having, Kubernetes doesn't mandate it, but it allows you to, it's a recommendation to have like 3 worker nodes running, just so that it can scale out in a much easier manner. And so here I kind of show, I have 2 nodes, but the pods kind of run inside of those nodes, and it has the Docker engine running as well. Kubelets are running on each of these nodes. That's what actually communicates with the API server and does, the dirty work of deploying pods, etc. And then you have kubeproxy, which is the proxy that allows you to actually take those services and, allow for communication to come through via the internet, etc. We also have etcd that I forgot to mention. Etcd is like the database for Kubernetes, and that's the thing that's used to store any kind of state information. So one of the things that a lot of folks, actually going back to this diagram, when you install and run Kubernetes, you're kind of responsible for running all of these, the worker nodes as well as the master node and all of the API server, and scheduler, etc. So you or your DevOps team are kind of responsible for all of it. So once you go into more of like a managed service, so on from an OCI perspective, we have a couple of services for this. We have an OCI registry. So instead of using Docker registry or any other registry that's out there, you can use the OCI registry, also known as OCIR. And then we have a managed Kubernetes service called the OCI Container Engine for Kubernetes. And so we also call it OKE for short. OKE actually handles your cluster management, your high availability, and your dashboard. So those are things that from a developer or from a DevOps team perspective, like that's not something that you necessarily have to manage. That's something that Oracle Cloud and our teams at Oracle Cloud will manage for you. And then inside of your tenancy, that's kind of where your worker nodes will go. So you can build VM-based clusters or bare metal clusters, kind of whatever you want to do, and run your applications. So you're spending more time actually with your applications versus doing all the dirty work of managing your cluster, etc., and figuring out how to scale that, etc., and all of those things. So if we break this down, we talked a little bit about architecture, but kind of how does it look like from a deployment perspective? This is a quick example of the actual YAML. So I talked about deployment earlier. And so this would actually be your deployments YAML. And so we have, a bit of metadata over here initially, and then you have the section starting at line 5 for the spec. And so the spec has selectors, labels. It has one replica over here. And the template in here also has a spec associated with that. And then you have the container section at line 15. And this container, we give it a name. We call it data service. And the image is, Jim Bob data service 1.0. So this is actually data service 1.0 is the actual Docker container that we would deploy. And then, I've tagged this as a version, so you can also version your services, etc. Once again, we expose port 5000 over here because that's the port we want to, expose because that's what we want folks kind of communicating with inside of the code. So from a Kubernetes point of view, we would say container port over here. So that's how kind of like everything would all work in from a Kubernetes standpoint. So if you're migrating from the old world, you're kind of coming from 3-tier architecture to something today. This is what we had shown earlier. Microservices and Kubernetes. This would become your load balancer layer would still be the same, but then from a server's perspective, you'd still have like different services that end up handling a lot of your workload. And then it would still behind the scenes talk to a database or a queue or really whatever you need. So the one thing that comes up a lot here is, folks kind of look at this and they're like, well, this becomes a state machine. So, containers do end up solving a problem, but there's also like this whole platform consideration that comes into play. Like you need a DevOps team to help you kind of manage your whole container platform. But for a lot of teams that only have developers, the question is like, how do you actually go about it? What do you need to do? And so that's a little bit of the friction behind using containers or Kubernetes in your workplace. And for those folks, there's a thing called serverless, where serverless is more, it's more developer driven. It follows an event-driven architecture, where you're not really worried about the infrastructure underneath you, more kind of worried about your code specifically. It automatically scales on demand, so regardless of whether you're calling your function 10 times a second or a million times a second, behind the scenes the infrastructure will scale on demand. The billing is a little bit different from traditional billing models where you might be billed by the hour or by the month. This is billed just for your execution. So if you have a bunch of executions at one time, the billing kind of depends on that. And also it's fault tolerant and highly available. So kind of taking a look at it, we looked at this earlier, microservices and containers on Kubernetes, you have the load balancer and services, etc., might be backed by a database behind the scenes. And if you compare this to the serverless model, here you just end up calling, you might still have a load balancer in front of you, but you just end up calling a service or a set of services behind the scenes, and you don't necessarily care as much about the infrastructure of where these things kind of run on. You just care that the services are available and you're ready to talk to them. So a lot of times folks kind of think of serverless more as a spectrum, going left through right. You are more aware of your infrastructure on the left, and then on the right-hand side, where you kind of talking about managed serverless platforms, you don't care about the infrastructure at all. So kind of stepping through it, you have container orchestration on the very left, where you're not necessarily you actually care about what you're running and where you're running it on. And then you kind of step through it where you might have like a managed Kubernetes service like OKE, etc. You might have container services, on Amazon you have like ECS, Fargate, etc. If you're using Oracle Cloud, you have Oracle Kubernetes Engine, where the managed service helps you, do all the provisioning of your containers, abstract some part of the infrastructure, but there's also infrastructure that you actually need to care about, like the the worker nodes that you're using yourself. And then you kind of go to a do-it-yourself functions as a service, where this is, OpenFast or OpenWhisk, etc. Those are things that you would install on your own Kubernetes cluster and have them running. And then you go to the managed serverless platforms. So in the Oracle Cloud use case, you'll have the functions platform on OCI. How does this work? So it's relatively straightforward. You upload your function source code. You might have a CI/CD platform that uploads your source code to the cloud. You configure a function trigger. So this is where you say how do you actually invoke the function, and then based on that trigger, the function is invoked, and then you kind of build for the execution time and not necessarily the time that you're waiting to actually get that function invoked. So from a platform perspective, in most use cases, you have some kind of event source that triggers a function execution. So your function actually goes and executes, and behind the scenes, it might be sitting on Kubernetes or Docker or whatever, which might be residing on, compute that uses some kind of networking and storage. But those are things that you don't necessarily care about. You just care about what your code is executing in that case. And behind the scenes, you might actually go and call a backend service. So your function might be, hey, run a nightly report to send an email. So you might be using like a backend email service, for example, or running an analytics job, or saving off something to a database, etc. So, coming back to the idea of is it really a spectrum or not, that it's really not, because you can do all of the stuff here that's kind of grayed out, but really when you're using a managed service, regardless of whether it's Amazon Lambda or using Oracle Functions, etc., you kind of trust the provider to run and do all the execution stuff for you. And you spend your time on the most valuable part, which is your business logic or your code. So kind of moving on to, more specifics of what serverless is not. It's not really magic. A lot of people struggle with this concept of, hey, how does it work, etc. It's more of an infrastructure decision or choice that you make. It's really good from a greenfield perspective, where you might not have any infrastructure. You're kind of coming in, want to design something, so you can use serverless as as a platform to kick off a lot of your workloads, etc. But you still need to actually do the design work up front. So there's some amount of work to do over there. A lot of enterprises come into this from a brownfield perspective, and in those scenarios, you still kind of need to break your monolith apart before you start using something like serverless or start using Oracle functions, etc. So to summarize, like really nothing is free. You still have to kind of take the paradigm, break it down a little bit into your own use cases, and then build out. So functions in serverless, microservices are kind of implemented as functions. And with microservices, applications might be comprised of many functions. This is actually an interesting perspective where, before you might have one code base, and it might have, even for a single application, you have, a dozen different endpoints that an application might have. In the functions scenario or in the serverless scenario, you could potentially break all of those things up into different functions altogether, or into different serverless modules altogether. So that's a choice that you can make. And, sometimes it depends on how you want to architect your applications. Developers, in some cases, like to go one extreme where they have every different endpoint ends up becoming its own serverless function, versus in some other scenarios, you kind of couple things together a little bit more. And functions end up mapping to events. So whether it's an API call or some kind of object store action, etc., they still end up mapping to some kind of event, either an event that triggers it or behind the scenes it kicks off an event. So I touched on this briefly. From an Oracle perspective, we have the FN project. So our serverless platform, the Oracle Functions, is actually based on the FN project. And so if you want to kind of go and read the source code, it's all open source, so you can kind of take a look at it. It's a container-based function platform, so it works really well on Kubernetes if you want to deploy this on top of Kubernetes, etc. And it's cloud agnostic, so you can kind of run it whether it's on-premise or on the cloud. It doesn't really matter. And, it's super active, so go check it out on GitHub. And from a cloud perspective, this is where people use Oracle Functions. It's fully managed serverless. It's based on the open source engine of the FN project. It's fully integrated with OCI, and it's container native. So, you can actually bring containers that allow you to run them as, serverless functions, multi-tenant and secure. But remember, when you're using serverless in general, it's pay per use, so you're paying for the execution, not necessarily the idle time. And since it's based on containers and open source, there's no necessary lock-in to actually having to do this via using some other functions platform, for example. So here's a quick example. So in the function example, we can take our little handler over here. So instead of importing something specific, this is Python once again. We're importing the FDK, or the Function Development Toolkit. And so we have the handler. This just returns a message of meaningful data. And lines 8 and 9 in here, it allows the FDK handle, and you're passing a handler to it. So what happens is when this is executing behind the scenes, the FDK.handle, so that'll take whatever handler code you have and execute that code behind the scenes. So probably the most common question that we get is, serverless sounds really cool, but what can I actually do with it? So from an implementation perspective and kind of what we've seen customers use serverless for, it's really good for web and mobile backends. Anytime you're trying to build an API, whether it's a front-end API, a back-end API, functions actually fits really well for that. Real-time processing of files or streams, when you have a lot of like bursty traffic, serverless works great. Batch processing, and also a lot of people use this to kind of like glue different pieces of infrastructure together. Think of if this then that perspective, or if this then that use cases where you're like, okay, I need I want to watch my infrastructure, and if this thing triggers, I want to send off an email, etc. So really good to do kind of that. And once you start using it, you can kind of find like different use cases for it. So we'll kind of wrap up here a little bit, and we'll talk about some high level ideas, and come close to an ending over here. So from a very high level perspective for cloud native, don't do what you don't have to do. Pick your problem and solve that problem specifically, and don't worry about all the rest around it. Lean heavily into the APIs, and when you're developing, especially if you're coming from the dev side of the house, try to simplify. Don't over architect. And then plan ahead for observability, because regardless of whether you're using Kubernetes or using containers or using serverless, etc., the observability, logging, monitoring, the mindset for that is a little bit different from traditional applications. So choose a pattern that helps you minimize. So less is more. Shoot for a single handler per module. So a lot of times when we're writing large enterprise applications, we have a lot of handlers in a single module. Try to break those up a little bit. If one function does more than if it has five or six different tasks or whatever, consider breaking that up into separate functions altogether. It's better to proliferate than to decompensate. And we talked about observability before, so observability and triage become easier to define at the boundaries than if you're trying to do it another way. So continuing with the simplification theme, simplify your application estate as well. Events can and probably should be defined or should define application boundaries. So think about the events that are either triggering your functions or triggering your handlers, and try to create boundaries based on that, and share libraries between functions and applications, and not necessarily the context. So you don't want to share your state specifically between a bunch of different things, but definitely share your the functions that you have. And coming out to like code reuse, so serverless functions, on some platforms, they were zip files, and now most platforms you can kind of expose a container image to you, so you can kind of reuse the same image across different, whether it's serverless or Kubernetes, you could reuse the container image there. Some folks end up using layering, so you can use some layers for Kubernetes and some layers from functions too, but that ends up being a little bit more complicated. And for Oracle functions specifically, it's container native, so the image is yours. You can kind of do whatever you want with it, and you can also end up reusing that with Oracle functions. So probably the most important question that people ask, or I guess the second most common questions, is like, should I do microservices or should I do serverless? So to kind of take one perspective on this, if you look at it from a serverless point of view, serverless is a quicker path to going cloud native. So for some applications, you might be able to go full serverless and not have to worry about your infrastructure at all. So that's great if you have those use cases. And then it also enforces you to follow best practices with respect to cloud native, whether it's logging, monitoring, observability, or what have you. Serverless kind of forces you to do that, and it allows your development teams, in large shops with a lot of developers, it allows the developers to be a lot more productive quicker than trying to figure out, hey, how do I make Kubernetes work? How do I make my environment work, etc. You're not spending a lot of time doing that. Now, from a counter point of view, if your team isn't ready to go to fully let go of your infrastructure, so in other words, if you have a larger DevOps kind of team and you're not necessarily you don't have as many developers on there, and you're either required to manage your Kubernetes or like manage your infrastructure, then Kubernetes might be a better approach. Still kind of consider manage Kubernetes versus doing everything yourself. And then be prepared to own your services in production. So today it's more common for developers and enterprises for everybody to, own their own services, for developers to carry around pagers, etc., to be on, on-call rotations. So that's something that it's the kind of the world we live in today. So be prepared for that. So let's do takeaways from all of this. So probably the first thing is, I've talked about cloud native. So I've talked about containers and I've talked about serverless. So these are not really mutually exclusive approaches. And sometimes people end up using both. Like I've seen teams and organizations where some parts of the infrastructure is done with serverless and the other part is done with Kubernetes. So you can kind of like mix and match things together. I wouldn't recommend mixing and matching day one, but work on one thing, figure it out, and then if you actually need the other thing as well, then consider using that. But they kind of like mix together pretty well. Applications and services, which require specific infrastructure components, are likely to remain in the managed container space for some time. So if you really need, a specific kind of instance, or you really need GPU or something like that, it'll probably remain in the container space for a while, because I think it'll take some time for serverless to come up to that speed, and it'll just take, containers end up matching more to the infrastructure underneath it than serverless does. If you're, writing a lot of APIs, or if you're writing a lot of backend kind of implementations, you should really consider serverless upfront, because I think it'll save you a lot of time from having to deal with the infrastructure behind the scenes. And finally, embrace the design paradigms. I talked about 12-factor applications before, and I talked about some other design considerations like through the talk. So definitely, embrace the design paradigms that we have, because all of those things will help you kind of go and build better applications at a cloud scale. So with that, I'll end up. If folks have questions, feel free to put it in the little question window, or feel free to reach out to me on Twitter. Thank you so much.